Look at this model on the right. Look at it go. Can streaming continuous information. It's going on forever. Look at it go. Not even running out of memory. It's amazing. Yeah. Anyways, this is StreamingLLM. It's a paper that came out a few days ago. And yeah, you can see it basically allows a model to stream, to do inference continuously. And let's check this out. Do they look fine? Yeah, the output looks fine. It looks like output. So yeah, streaming LLM, the goal is to take a large language model and allow it to continuously stream information that makes sense, but also don't run out of memory. So normal LLM will run out of memory and it'll start making up gibberish as it gets longer. But streaming LLM fixes that. So yeah, let's get into it. First off, normal LLM, normal attention. Let's go over that. If you're already familiar with that, feel free to skip. But let's say we have the sequence. So this works on sequences, and I'm just going to do like a high-level overview, enough to have it make sense. If you're more curious about how attention works in full detail, go look at like an attention is all you need video. But at a high level, if we have, say, the words the cat sat, normal, good old sentence, then you have these three words, and each of these words are represented by a token. So it would be 3 tokens of dimensionality d. So you represent the sequence as 3 tokens of dimensionality d. So you have this n by d sequence where n is equal to 3. So this is how you represent the sequence. And for attention, basically what you want is you want to route information from token to token. So let's say we have these 3 tokens here. Actually, I'll just represent it like A, B, and C. Then we can construct this matrix called the attention matrix, which looks like a n by n matrix. So this would be n is equal to 3, and n is equal to 3. A, B, C, n is equal to 3. And basically this tells you how much information you're going to be routing between tokens. So the word A, so let me bring this down here. Right here. So this first word A, it sends information to itself, obviously, and we're going to have these attention scores. Now, these attention scores are going to be normalized over the token, which or over the row, which we'll get to in a second. But yeah, the word A attends to the word A, and you receive some value. Now, the way you train this thing is the tokens cannot look ahead, and that's just for training purposes. So this token cannot look into the future and send information to the future. However, tokens in the future can basically, can receive information from tokens in the past, but kind of thinking about it, tokens from the past cannot send information to the tokens in the future. So we mask off these parts here. And that's just how you train it. You train it this way so you can effectively parallelize your training. And yeah, if you have this upper triangular mask, which is always going to look like this, then this token A cannot attend to future tokens. The token B cannot attend to future tokens either. Notice how it can't attend to C. But token C can. It can look at all past tokens. So the token B, this is cat. Maybe the word cat, the word cat and the word the aren't very useful. So maybe this gets like a 0.9 score. So B is attending to B, but the token A doesn't really need to send much information to the token B. So maybe that's 0.1. So it's not sending that much information because the word the is kind of useless. Now, for the token C, so you can think of it like row-wise, the token C, it needs information from itself. Maybe this is 0.6, but it also needs to know what is doing the sitting. So this is the word sat. So what is doing the sitting? So it needs some information from token B, and maybe we'll make this 0.35, and then it needs practically no information from the word the. So that's our attention matrix, and this is essentially a routing of information. So now we have a new token. So our new representation for the word A is going to be A prime is equal to, and I'm skipping over a lot of detail here, but essentially A prime is going to be equal to 1 times A plus 0 times, the mask here indicates a 0, 0 times B plus 0 times C. So the new word for A, the new representation for the word A, is essentially just going to be A. So A prime is equal to A, and that's because we have the mask there, not allowing it to attend to the future. Now B prime is going to be equal to a little bit of the word A, because why not? It's just kind of arbitrary, plus a majority of itself. Now, the important case, the word C, is going to be composed of a little bit of the word the, but it's going to be composed of now mostly what it was before, but it's going to have information from the word B now, from the word cat. So now maybe it can infer what is doing the sitting from this information here. So 0.35 times B plus 0.6 times C. So this is attention. Basically, you're doing this dynamic routing of information where the tokens send information, or the tokens kind of receive information from other tokens. The word C is receiving information from all other tokens. The word B is receiving information from the word the, and the word the is receiving information from, well, itself, because it's the start of the sequence. And you keep on going. So maybe we had the word on, then D prime, the word on, if D is on, would be a combination of the, cat, and sat. So maybe, I mean, that's probably not important, but if the next word E was mat, maybe mat would get information from the word sat. This is an action on the word mat, and what is on the mat, cat is on the mat. So maybe it gets information from B and C. But you can kind of see, you construct this matrix, and it sends information dynamically based off what these tokens are. So that is attention. And the way you normalize these is through a softmax, which we'll get to later. But this is basically a high-level overview of attention, and it's how you are going to do inference. If you want to do inference, you would have this token would be your last token, and you send this through multiple layers over and over and over again. So maybe our last layer is like C, it's like like 30 primes or whatever. So you have like 30 layers. So it'd be C prime, 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 whatever you want to call it. But basically you do this attention 30 times and you result in this output C. And this output C will predict the next token in the sequence. Maybe that is the word on, because that's how you do your autoregressive modeling. So this last token here is predicting the next token in the sequence. And that's all you're doing in attention in a transformer. So that's a high-level overview of attention. Now, what do they do? So they basically say that there are multiple ways to do inference in attention. So this is our attention matrix, and you're going to see this attention matrix all throughout this paper. So this attention matrix here shows that you have these tokens here, and these tokens are doing their attending. So this token is the word the, this token is the word cat, this token is the word sat, and so on. You have more tokens. And this token right here, the last token, is the current token being attended to, the current last token, which is going to do the prediction. So this is our predictive token here. This token needs to receive information from all the other tokens, so it's a pretty important token. Now, what you do in practice is you actually cache the keys or the keys and the values. So if we go back to our example here, you actually have your sequence A, B, C, and you construct 3 different versions of this using a weight transformation, so using a linear layer. So this would be AK, BK, and CK. That's not a K. And then you would also create a query, or your queries, AQ, BQ, and CQ, and then your values, AV, BV, and CV. These two here are what construct this. So these would be your Ks, and these would be your Qs. So you construct the matrix from keys and queries. So this would be our keys, and these would be our queries here. And the values would be these ones here. So this would actually be AV, AV, BV, AV, BV, CV. But you can think of them as just the initial tokens in the sequence. So that's the full attention, but you actually cache your keys and your values. So you actually cache these so you don't have to recompute them. And basically the idea is, so for example, whenever you initially calculate A, you would store this in the sequence from now on. So let's say we have these tokens here, A, B, C. Whenever you compute the token D, you don't recompute these tokens here. So you don't do this sum here. You just cache the values. And the reason you would cache the values here you wouldn't cache those values. You would cache the keys and the values down here. And the reason you cache these values is so you don't have to recompute them. So you can see that they state that here. You cache these tokens. So you're not doing anything with them. They're going to be the same token. So you don't redo the computation because you don't really have to. And it's going to be a similar. So if you did recompute it, it'll be similar as if you didn't do as if you just cached it. So it works out in the end. You just cache these tokens here, and this last token here is going to be the one that gets attending to. So this information will be routed here. The other tokens are cached, so you actually cache the information instead of recomputing it every time. You only recompute this last one. So how can we make this more efficient? So you might be able to see, and you probably know, that attention is n squared. So you construct this matrix here, which is an n by n matrix. And the problem with an n by n matrix is two things. One, you have to store n squared information. You have to store n squared data, and that will blow up your system. The other, because it takes up too much memory, the other is it takes n squared time to construct this matrix. So to do a matrix multiplication, n by d by n, this would be O of n squared d. That's the complexity of this matrix multiplication, and it's quadratic in terms of the sequence length. So as the sequence length grows, it takes longer to do the computation, but it also takes more memory. So you have to keep on storing tokens. Now to get past this, there's this thing called window detention. So after you're done training, I guess you can do this during training as well, but after you're done training, what you do is you evict a certain number of tokens here. So you evict these tokens here in the attention matrix, and you only keep these tokens here. You can see that there's like a window size of 4 here. So this window size here would correspond, this would be A, B, C, D. So these are your first 4 items in your sequence, and then you have E, F, G, and H. So you only have context for the last 3 words in this case, since the attention window is 4, to compute your next word. And the problem with that is you basically just throw away a ton of information. And you can see that this is actually, it's better complexity, but it also is garbage in terms of perplexity. And whenever you see PPL, that's basically the loss. It's how well the model is doing. You can think of it as the loss. It's just it's a transformation of the loss. I think it's an exponential of the loss, but perplexity, just the lower the better. Now, if we look here, a sliding window attention where you recompute the cached values, so you're no longer caching them, the perplexity is much better, and that's because like the cached values don't necessarily, they're not the exact same as if you were to recompute them. So you recompute them, you recompute this information here, and it works better. The perplexity is higher, but it requires, it's on the order of t L squared. So you have to recompute the cached values, and that increases the complexity. So They propose streaming LLM, and streaming LLM is what we'll see later. But basically, you do the exact same thing as the window detention, except you have these tokens here, these yellow tokens, and these yellow tokens are what they call these are sinks, attention sinks, and we'll see why in a little bit. So that's the idea. The idea is you have this window detention, and you want to add these new tokens here, and these new tokens basically allow it to throw information into these sinks, and we'll see why that's important. But that's the idea. So that's sliding window attention. Now, what is the problem with sliding windows? So if we look at the softmax operation, so the softmax operation is what normalizes every token. So if we had, say, I guess in this case it wouldn't really matter, but yeah, it basically normalizes each row here. It normalizes row-wise because we're computing this output as a combination of them. So you can think of A prime, B prime, and C prime as like it's multiplying by a distribution. So you have this, so you have your distribution here. This is essentially your distribution, and that tells you how your output token is going to be created. So your distribution would look something like this. This would be A, this would be B, this would be C, and this is basically what C prime is. So it's a distribution, and it's a distribution because of the softmax. Now, what they say is, let me get my highlighter. They find beyond the bottom two layers, the model consistently focuses on the initial tokens across all layers and heads. So this is an interesting phenomenon they find. If we look at this part here, yes, here, I think, yeah, if we look here, you can see that it just, so red is high, blue is low. You can see that it puts a lot of information on these first tokens here. So that's these tokens here, the 0th token, yeah, puts a lot of information on the first tokens here. Puts a lot of information on these first tokens. That's what it's saying right here. So a lot of information on the first tokens. And they say that the implication is clear. Removing the initial key value tokens will remove a considerable proportion of the denominator from the softmax in the attention computation. So whenever you're doing sliding window, so whenever you don't do sliding window, there's a lot of attention going into these first tokens for some reason. For some reason, there's a lot of attention going to the first tokens in the sequence, no matter what the sequence is. The sequence can be anything, and there's a lot of information going to the first tokens in the sequence for some reason. This is a phenomenon they find. And if you remove this, then the statistics of the softmax kind of get all messed up. So they say removing those values leads to a significant shift in the distribution of attention scores away what would be expected from a normal inference setting. So whenever you remove it, you have, so in attention, you have this denominator, and whenever you remove this large value, this sum below the denominator becomes a lot smaller, meaning that the values that would be, say, mediocrely large in magnitude are much larger in magnitude, meaning that they will have a much larger attention value. So they claim that this is a big problem, that removing this initial token here, or removing some of the initial tokens with very high attention scores before normalization. This is after normalization, but before normalization, before the softmax normalization, basically messes up the statistics of the distribution because since they're no longer there, it messes up this denominator. So that's the idea. Removing these messes up the denominator, it messes up the statistics of the distribution, and that's what makes the model go all crazy. And if we look here, KV cache size, whenever, so orange is normal window attention, red is streaming LLM. So whenever you get to the key value cache size, this is whenever you start removing the first tokens, the attention scores blow up, or like the perplexity blows up. And that's because the statistics are messed up. You can see here, it blows up again. It kind of stabilizes for the Pythia model. For Falcon, what was blue? Oh, blue is just dense attention. So yeah, dense attention is just not very good. But the windowed attention, I guess in this case, it doesn't actually like blow up. It gets larger, as you can see here, but not too much larger. And then here it blows up again. So you can see removing these initial values, which they term attention sinks, just places where it throws a lot of information, is a problem. And it's because the statistics of the distribution become bad. It becomes not what the model has seen before. And they say there are two possible explanations for the importance of these initial tokens. One, either the semantics are crucial, so the first tokens are very important for some reason. Who knows? Maybe you trained on some weird data set and the first tokens happen to be very important. However, a more likely explanation is the model learns a bias towards the absolute position. To distinguish between these possibilities, they conduct an experiment. Table 1, where the first 4 tokens are substituted with line break tokens. The observations indicate the model still significantly emphasizes these initial line break tokens. So the idea is if there is a bias, then replacing the initial tokens with a random token, in this case a new line, will not mess up performance that much. Now if we go here, we can see that just removing those tokens, it does terrible. Now if you add the context of the first 4 tokens back, and remember, we said that the first tokens, whatever those may be, had a lot of attention going to it for some reason. Now, if we add those tokens back, so we just add the first 4 tokens, let's say we had the sequence, say, A, B, C, D, E, F, G, H, I, and let's say our window was this, then normal window attention, you would only take these tokens here. However, in the new attention, they take the first 4 tokens here, and then they scrap these ones. So these tokens, which were getting high attention values, are appended to the beginning of the sequence, and then you go from there. And these are always in your output. These are always in your attention sequence. And they show that just adding those back does better. However, if those tokens were semantically important, then replacing them with new lines, so this wouldn't be A, B, C, D, this would be new line, new line, new line, new line, and they're always just new lines, would go back to the original perplexity, or at least increase a lot. But you can see that replacing them with a new line gives you basically the same perplexity. Not much has changed. And that means that there's something weird with the positional bias here. There's a positional bias with these first tokens here, and it's not because those tokens are important, it's just because the position is important, and it's basically just throwing information there. Now, continuing, they say to explain why the model focuses on these initial tokens, we introduce the concept of an attention sink. So they term these initial tokens that receive a lot of attention scores, receive high attention scores, are attention sinks. The nature of the softmax function prevents all tokens from having 0 value. That's because it's a distribution. They don't have 0 value because it's a distribution. So you normalize it, doesn't have 0 value because of the softmax. And this requires the aggregation. So this requires aggregating some information from other tokens across all heads and layers, even if the current embeddings have sufficient self-contained information for its prediction. So there's this idea that basically you need these tokens that'll pass information from layer to layer. So there needs to be these tokens, whatever token those may be, there needs to be tokens that aggregate information from layer to layer so that you can kind of pass that value back out. And maybe this has some meaning to the transformer, but you need these tokens to just send information to. And it also helps with your normalization here. But yeah, basically the model will send a lot of information to some of these initial tokens because it requires, it needs to aggregate some information across layers. And the only way to do that is if you have these kind of trash tokens that just accept information, and you can kind of, I guess you can kind of throw information in, kind of keep on compiling information into these tokens and take information out. I guess you can kind of think of it that way, like a read and write operation in a way. You can kind of think of it that way, what these tokens are used for. And since the model, you can think about it, the model will always have like the first 4 tokens in the sequence. And since it knows it always has those first 4 tokens in the sequence, it always knows it can write to those first 4 tokens, no matter what they are, because it knows those positions of the tokens. So the idea is it can write to those because it needs to write and read somewhere, basically. Then they say the model tends to dump unnecessary attention values to these tokens, and a similar observation has been made elsewhere. So that's the reason. It just needs to dump information somewhere. So yeah. Now adding these first 4 tokens. So if you just they say here, rolling key value cache with attention sinks. So basically all they do is they add the first 4 tokens. So we can see in this diagram here, we have these 7 tokens. So this is our window size. This is our, these are our attention sinks. And the attention sinks are just the first 4 values in the model. So if we had the cat sat, and then you continue on, and then you have tokens A, B, C, D, then you would keep the first, in this case, it would just be 3 tokens. You would keep these tokens, and then you would do your sliding window after that. And you can see the sliding window does not retain token 4 or token 5, or you just remove those. And yeah, that's kind of all they do. They do make an important note. So the way they do the positional encodings is not like you would think. You may think that the positional encodings would be sequential. So it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you remove this one. It's not like that. What you do instead is you do 0, 1, 2, 3, and then you skip here. So this would be token 4, and it's like you start your sequence here instead of skipping all the positional embeddings here, 5, 6, 7. They say that's an important thing here. If the current cache has tokens 0, 1, 2, 3, you skip 4 and 5 here. And the process of decoding the 9th token, the positions are assigned 0, 1, 2, 3, 4, 5, 6, 7. So you don't skip any positional encodings, rather than the positions being the original text, which would be 0, 1, 2, 3, without 4 and 5, and then 6, 7, 8, 9. So that's an important note they make. Yeah, so that's the solution, and the solution works pretty well. If we go here, we can see that adding, so 0 tokens, this is normal inference with the sliding window, does garbage. Adding only 1 token of information, so only keeping 1 of the tokens, it does way better. It's not even close. And they show that adding 4 tokens pretty much does as well as it can possibly do. Adding 8 does a little bit better, but you don't really need it. So adding 4 tokens is sufficient to get equal, or to get really good perplexity. So that's all you need to do. Just add 4 tokens to the beginning of the sequence and change the positional encodings, and you got yourself a model that can do inference forever, because it also throws the information away from the middle of the sequence. So they go on to say, what if we pre-trained the models with attention sinks? Then maybe we can fix this problem in the first place. So potential remedy can be just adding the sync token which would serve as a repository for unnecessary attention scores. And basically all they do is they append one token to the beginning of the sequence here. And yeah, or you do this for training as opposed to doing it just for inference. And if you do it just for training, then it does better. Well, yeah, it does better, as you can see here. This is, so you have your vanilla one, you have your zero sync, and you have your learnable sync. Zero sync, they say, is if you've read the paper softmax off by one, then you know that they have, you just add one to the denominator. And the learnable, this is like a learnable version of that. It does better, as you can see here. It does, yeah, it does better. Yeah, and all you need is one token, one learnable token. So yeah, you can fix the problem just by adding one token to the beginning, and it doesn't have this issue anymore because it has this token it can throw information at. They say somewhere over here that they believe this problem exists because models such as Llama did not include a consistent starting token across all input samples during pre-training. So they were kind of wondering why this problem was here to begin with, and it's because these models didn't append like a sync token or a \s or a starting token to begin with in a consistent manner, but doing so fixes the problem. So yeah, just add a start token and it fixes it. And yeah, they have some results showing that if you just add the sync token, it does better than if you don't add the sync token to the beginning whenever you train it. And then they have these results here. If you pre-train without the sync token, you can see that it sends kind of it has the attention scores going to the beginning in some heads, but in other heads it's kind of like all over the place. But it has a lot of information to the first few tokens, while it's a lot more uniform if you pre-train with the sync token here. It sends a lot of information to this first token only, and then it's very uniform otherwise. So this token is being utilized, as you can see. So interesting, just add the start token and it does better. They say here, without a sync token, models show local attention in lower layers and increase attention to initial tokens in deep layers. With the sync token, it is clear attention directed at it across all layers, effectively collecting redundant attention. So collecting this information so that the softmax works out better, so that the statistics are actually correct. And then they do some ablations and stuff. But yeah, that's basically the paper. Just add on a few tokens to the beginning and you get this model that can do inference forever. That's the paper.